Artificial intelligence is changing the world, and large language models, or LLMs, are at the forefront. These massive computer programs are like digital brains, capable of writing, translating, and even understanding complex information. But there's a catch. They're huge, so huge that running them requires massive computing power. That's where model compression comes in. There are 3 compression techniques have been applied to LLMs: quantization, pruning, and knowledge distillation. In this video, we will cover quantization. So what is quantization? Technically, quantization is a model compression technique that converts the weights and activations within an LLM from a high-precision data representation to a lower-precision data representation. Let's simplify this. Imagine numbers on a giant ruler. Normally, we use a very fine-grained ruler with lots of decimal places. This is like using 32-bit floating-point numbers in computer models. Quantization is like switching to a coarser ruler, snapping those numbers to whole integers like 8-bit integers. It makes the numbers simpler and smaller. Another great analogy for understanding quantization is image compression. Compressing an image involves reducing its size by removing some of the information from it. Now, while decreasing the size of an image typically reduces its quality to acceptable levels, it also means more images can be saved on a given device while requiring less time and bandwidth to transfer or display to a user. So what are all the advantages of quantizing large language models? 3 reasons: smaller memory footprint, faster response, and lower processing requirement. It's basically shrinking them to small language models. With smaller size, quantized models take up less storage space as well as lower memory footprint. The lower memory footprint produced by smaller models also makes them more scalable. As quantized models have fewer hardware constraints, organizations can feasibly add to their IT infrastructure to accommodate their use. Integer calculations are much faster for computers than floating-point ones, meaning models can react and respond more quickly. Smaller models use less power to run, which is important for mobile devices and cutting energy costs. Of course, nothing is perfect. Quantization slightly decreases the model's accuracy, like describing a color as red instead of crimson. For most tasks, this trade-off is worth it for smaller, faster models. It's been discovered that instead of using the 4-byte FP32 precision, we can get an almost identical inference outcome with 2-byte FP16 half precision, which halves the model size. Now that we have covered what quantization is and why it is beneficial, let us turn our attention to different quantization methods. There are 2 main approaches for quantization. Post-training quantization, PTQ, is done after training the LLM. It's simpler to implement but may lead to a slight accuracy drop due to the conversion process. Quantization-aware training, QAT, is integrated into the training itself. The model is trained while simulating the lower precision it will be used in, making it more robust to the conversion. But if you are not the one developing the model, then PTQ approaches are best suited. In this section of the video, we will talk about 3 widely used PTQ techniques: Q, LoRa quantized low-rank approximation, PRI LoRa, product of row, independent low-rank approximations, and GPTQ, general pre-trained transformer quantization. Q LoRa. The key idea with Q LoRa is instead of quantizing the whole massive weight matrix of an LLM, break it into smaller, more manageable chunks and quantize those. To give you simple analogy, imagine a huge Excel file. Instead of compressing the whole thing, Q LoRa splits it into smaller workbooks and compresses those individually. This gives fine-grained control over how much compression you apply to different parts of the model and better balance between accuracy loss and size reduction. PRI LoRa extends the idea of breaking down the weight matrix even further. It represents the matrix as a multiplication of smaller, independently quantized matrices, like Q LoRa. But instead of workbooks, PRI LoRa splits the giant Excel file into individual sheets and then into independent rows on each sheet for compression. This technique gives even greater compression potential than Q LoRa and also provides more specialized hardware acceleration. GPTQ combines quantization with knowledge distillation. Think of it as a 2-step process. Step 1, it trains a huge teacher LLM, and in the next step, distill its knowledge into a smaller quantized student LLM that mimics the larger model's output. It's like Master Chef teaches a student, the quantized model, their best recipes. The student may not have all the ingredients on hand, but they learn to approximate the final dish. This technique can achieve drastic size reductions and provide the power of large pre-trained models in a smaller, compressed format. To conclude, quantization unlocks the potential of large language models. It is an integral part of the LLM landscape. By compressing the size of language models with quantization techniques such as CLORA and GTPQ will help to increase the adoption of LLMs. It will remove the restriction of the vast memory and GPU requirements of full precision models and create more opportunities to experiment with the rapidly growing range of LLMs. Smaller quantized models can perform well on CPUs, making them ideal for applications that don't require the brute force of a GPU. This opens doors to deploying LLMs on everyday devices like laptops and even mobile phones, bringing the power of language processing closer to the user. Want to learn more about language models? Be sure to subscribe to our channel for more insightful content on emerging technologies and their impact on our lives. Don't forget to hit the like button if you enjoyed this video. Together, let's navigate the exciting frontier of innovation. Thank you for watching.